Problem number 4. Consider the differential equation dy dx equals x squared minus 1/2 y. Find d squared y dx squared in terms of x and y. Well, we know that this means a second derivative, and we already have the first derivative, so we'll just take the derivative again. So we'll have d squared y dx squared is equal to the derivative of x squared is 2x minus the derivative of 1/2 y would be 1/2 dy dx. And this says to have it in terms of x and y, so we're going to have to replace dy dx with what it is. So this will be 2x minus 1/2 times the quantity x squared minus 1/2 y. All right, so that will be worth 2 points. So if you did that right, we got our 2 points. Good, that wasn't so bad. I'm guessing if you didn't replace your dy dx, you'd probably get 1 point. All right, part B, let y equal f of x be the particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph of f have a relative minimum, a relative maximum, or neither at the point -2, 8? Justify your answer. Well, if we want to find out if it has a relative minimum, a relative maximum, or neither, first of all, we need to decide if it's a critical point, and then if it is it a minimum, maximum, or neither? Okay, so the first thing we need to do is take this and we're going to plug in the point -2, 8 for our x's and our y's. So we are going to have -2 squared minus 1/2 times the y value. When we do that, we do end up getting 0. So it is a critical value. So we generally, when we do this type of problem, we make ourselves an f prime chart or y prime chart, whatever, and put the critical value on it, which would be -2, 8. However, we're not used to working with critical values when we have the x's and y's. So we're going to do this a little bit differently. There's something that's called the second derivative test. So if the first derivative of y prime is equal to 0, we're actually going to be testing y double prime. We're going to put -2, 8 in there. So if we find the second derivative, which we already found, if we plug -2, 8 in there, we will end up getting 2 times -2 minus 1/2 times -2 squared minus 1/2 times 8. So if we find that answer is going to equal -4. So we found out that y double prime is less than 0. It was a negative answer. So if we get y prime equaling 0, which makes it a critical value, and if we find that y double prime is less than 0, that means that there is a relative maximum at that point. If we found out that y double prime was greater than 0, there would be a relative minimum at that point. And again, that was called the second derivative test. So we will say f or y, it doesn't matter which one we refer to it as, has a relative, it says does the graph of f, so we'll refer, I guess we'll call it f. F has a relative maximum at the point -2, 8, and our reasoning will be because f prime equals 0 and f double prime is less than 0. And again, I don't really think it matters whether we use y or f because they said that y is equal to f. So that was worth 2 points. Your conclusion that it's a relative maximum and y. So 2 points, there we go. Alrighty, part C, let y equal g be the particular solution to the given differential equation with g of -1 equaling 2. Find the limit as x approaches -1 of g of x minus 2 over 3 times the quantity x plus 1 squared. Show the work that leads to your answer. Okay, when we're finding a limit, the first thing that we want to do is just plug in the x value into the equation and see what happens. So if I plug that in, get the limit as x approaches -1, I'll have g of -1 minus 2 over 3 times -1 plus 1 squared. Okay, when I do that, g of -1 they told me was 2, so I end up getting 0 over 0, which means I get to use L'Hopital's rule. So if I use L'Hopital's, I'm now going to have the limit as x approaches -1. If I take the derivative of g of x minus 2, I'm going to get g prime of x, and the derivative of minus 2 is nothing, so I'll get g prime of x over 3 times -1 plus 1. Well, I will get, I forgot to take the derivative of it, sorry, 6x plus 1. Okay, and now if I plug in -1, I'll get g prime of -1 over 6 negative 1 plus 1. So again, on the bottom I get 0. And on the top, g prime of negative 1, to get g prime of negative 1, I know that negative 1 goes with y value of 2. So to get g prime of negative 1, g prime of negative 1, this is going to be the derivative of it, so we should be fine with that. It's going to be 2 squared minus, hold it, did I do that incorrectly? Yes, I did. It's going to be negative 1, sorry. Negative 1 squared minus 1/2 times the y value, which is 2. And if I do that, I get 0 again. Hopefully all those scribbles made sense. So we're going to use L'Hopital's rule again. So we're going to find the limit as x approaches negative 1. The derivative of g prime of x will be g double prime of x over the derivative of 6 times the quantity x plus 1 will just be 6. So g double prime of x, we are going to have to use the second derivative. So we are going to do 2 times the x value, which is negative 1, minus, I'm using the second derivative that we found way up in part A, then minus 1/2. 1 minus 1/2 times 2 all over 6. This will equal 0, and then we'll end up getting negative 2 in the numerator, and then in the denominator we have 6, so my limit will be negative 1/3. So we get 2 points for applying L'Hopital's rule twice. So we applied it once, we applied it again. Always make sure that you refer to that you're using L'Hopital's rule and why. So notice I did put 0 over 0 to show that that was good. And then we get 1 point for getting this right answer. So that problem was worth 3 points. Okay, part D, let h of x be the particular solution to the given differential equation with h of 0 equals 2. Using Euler's method, starting at x equals 0 with 2 steps of equal size, approximate h of 1. So we're going to start, we're going to make an xy chart on this one. We'll start with the point 0, 2, and I just need to get up to h of 1, just 2 steps. We're used to doing 3 steps, but it's just 2. So our first step would be 0.5, and our next step would be 1. So 1, 2 steps. So we just went by 0.5s. So if you recall, our first step, we just know that m is equal to delta y over delta x, and our m is our derivative. So if I plug in 0, 2 into our derivative on this left side, I'm going to get 0 squared minus 1/2 times 2. That will give me negative 1 equals delta y over delta x. The change in my x's is 0.5. That's my step size. I'll get delta y is equal to negative 0.5. So I'm going to subtract 0.5 from my y value, so now I have 1.5. Okay, so my next step, again, we'll have m equals delta y over delta x. Again, we're going to plug in our new point into the derivative, so we're going to get 0.5 squared minus 1/2 times 1.5, sorry. And then if we figure that out, that's going to be 0.25 minus half of 1.5 will be 0.75, so 0.25 minus 0.75 will be negative 0.5 equals delta y over our step size again is 0.5, so negative 0.5 times 0.5 will be negative 0.25, and so we're going to subtract 0.25 from my y value, and when I do that I will get 1.25. So it's said to approximate h of 1, so my h of 1 is approximately 1.25. All right, so if I used Euler's method, I got a point, and if I got the correct approximation, I also got a point. So this part was worth 2 points.